All right. Hi, everybody. Welcome back. Today, our lecture is going to be on classification. We've previously worked mostly on regression, but now we're going to work on classification. And specifically, we're going to do two algorithms called k-nearest neighbor and logistic regression. So, I'm Professor Wu. Let's get started. So, classification, we previously learned the concept of regression. In regression, we essentially predict a number within a range of numbers. So, what we are predicting of a continuous number was age of a baby or housing price, stock prices. These were the things that you could predict with regression. However, today we're going to move on and learn this thing called classification. In classification, instead of predicting a number, we're predicting categories. So is this dog or a cat, like a yes or no problem, right? Which letter are you showing? Like character recognition when you're looking at handwriting and you, as a picture, and you recognize the handwriting. Or does the patient have cancer? Yes or no? In classification, we have finite number of possible categories, and we want to pick essentially the correct one. So the very first algorithm is called k-nearest neighbor. This is really, really, really easy algorithm. Now, with k-nearest neighbor is a type of binary classification where you're just looking for yes or no answers. With binary classification, um, you only have two outputs, yes or no. Normally we have one or zero. Other times we have negative one or one, but the point is the same. It's just two possible options, right? And we want to predict if a data belongs to yes or no, given some kind of historical past data. So let's assume, as an example, that we have some historical data containing two factors along with if the student make it into a good college. So the two factors are grades and sport, and these are the scores. So these students, E and A, they did not make into a good college, and these ones, C and D, they did. Now let's plot them out. A and E are right here, C and D are here. Okay, let's look at this visually, here and here. Now, given this historical data, now I give you a new student B, which is at this point. If you just look at this picture, would you say that this student will make it into a good college or a bad college, right? Or not make into a good college? Okay, so I mean, visually, you will say that probably by looking at this point, you probably conclude that this student did not make into a good college. Okay, and then like what actually, if you think about it, what actually goes through our head when we make this kind of intuitive guess, what happened is when we what we do is we tend to look at other students with similar scores, right? You look at these students have similar scores and then use their outcome as a prediction. So this is a very simple pattern recognition. You look at what has happened in the past, right? When you see a new student, you look at what happened in the past, and then you look at the very similar students similar to B. What happened to them is probably what will happen to B, right? This is how K nearest neighbor basically works. We perform K nearest neighbor by picking K numbers of neighbors, the closest K nearest neighbors, and then simply classify the new point based on the common category. So over here, right? Like notice that B is significantly closer to E. So if our nearest neighbor is 1, then you will say this is my nearest neighbor, and whatever category E belongs to is what I'm going to assign B. Okay. 2 nearest neighbor, if K is equal to 2, then you pick the first nearest neighbor and the second nearest neighbor, and then give B the same category. So both of them did not make into good college. So, and then if you have 3, K is equal to 3. So over here, for example, if K is equal to 3, then you will have a good category, a bad category, and bad. And you will basically do a vote. Majority voted for good, voted for bad. Therefore, you will say the student did not make into a good college. Okay. So that's basically it. Like K nearest neighbor is a very, very simple algorithm. and it's theoretically simple to understand. It's really based on human intuition, right? You look at historically, this is what happened to kids like with these scores, and therefore, with these scores, this kid probably will result in the same way. Now, it's a very simple algorithm. It performs quite well for for simple cases. K-nearest neighbor is not a good algorithm if we have like high dimensional data. Now, K-nearest neighbor could be used for classification and regression. So we've looked at classification. In classification, you pick the most commonly occurring category, right? But in regression, you take the labels of the k nearest neighbor and then you average the labels together. So if these points, this point gives you a 4, this point gives you a 5, and you have a point in between, you will say 4.5, like that. So you can use k nearest neighbor also for regression. With k nearest neighbor, there are only a couple questions you need to answer ahead of time before using the algorithm. First, what should the number of k be? How many neighbors should you look into? We have two general rules. Um, Basically, you want to use square root of n. And square root of n is like the n is the number of samples. So square root of that is generally a good value you want to pick. Okay. And the second one is which distance norm should we pick? So when we measure the distance between points, should we do L1, L2, L infinity? So those are the like design decisions you will have to make before you perform k nearest neighbor. Most of the time, though, we use the L2 norm. Now, k nearest neighbor with the previous data, right? So this was the previous data, and then given a new student, what we do is we simply take the new student and measure the distance. So from B to E, B to A, right? Now let's use L1 known distance. So B to E is 1, B to A is 1, B to C's distance is 5. So you can see that the nearest neighbors are right here. And their result is right here. So you just pick the same result as the nearest neighbor. And that's it. So K nearest neighbor is super easy. And I think that that's good for now. Okay, we're going to move on to the second algorithm of the day, which is logistic regression. Now, logistic regression, we're going to continue for now to do logistic regression with binary classification. Binary. Okay, let's continue with binary. So we're still just deciding if it's cat or dog, yes or no. Okay, so that's binary classification. It's the simplest form of classification. It consists of two possible outputs, yes or no, dog or cat, right? And we normally represent the binary, like I said, 0 or 1, or sometimes we represent the labels as -1 or 1. The function that we use for binary classification the most is called the sigmoid function. The sigmoid function looks something like this. Okay, and when we plot out the sigmoid function, it goes from 0 all the way to 1. So the output of the sigmoid function is between 0 and 1. Okay, that's what the output. Now, why? Like we show in the graph that no matter what point you pick, you're always going to get a value between 0 and 1, and you want to take a second and think why that would be helpful for classification, right? Well, it's because this this sigmoid function can model the probability of one happening. Okay, because the probability of something is always a number between 0 and 1. So if you can get this probability, that's great. So we're going to say the probability of success is when x is equal to 1. And we're saying that it could be modeled with a sort of a sigmoid function. Not exactly the same. Remember the sigmoid was 1 plus e to the minus x. So we kind of changed this portion a little bit. So this is some kind of function, this right here. Similar to when we were doing linear regression and polynomial regression. This is some kind of feature map times w. Okay, so this is probably because this outputs a number between 0 and 1. This gives us the probability of success. So maybe success is 60%. And then if that's a probability x equals to 1, then the probability of failure is 1 minus zero point 0.6, which is zero point 0.4. So the probability of success is just 1 minus the probability of failure. Okay? Note that the probability of failure is 1 minus probability of success. The goal to find the weight, the goal here, right, is if you know the weight, if you know this, then in the future, you can always plug any point in and you will give you the probability of success. So as long as you can find the weight, the problem is solved. Right? Imagine if we know the weight, right? Then we can plug it in and we get some kind of probability. And if the probability is greater than zero point 0.5, like zero point 0.9, we will say, well, the probability of success is zero point 0.9, so it's probably a 1. But if the probability of success is a very small number, zero point 0.1, then we'll say it's probably a 0. Okay. So the idea of logistic regression, it's just like regression. In regression, we try to find some function in terms of W. Here we're trying to find also some function, but a probability function, a probability. And then similarly, we put this equation of a probability function into some kind of prediction error. So the goal is to minimize the prediction error by finding the best W value that goes in here. Okay, so that's the goal. All right. So once we know W, like I said, if we know W, we can make lots of predictions, right? And if the prediction is zero point 0.2 versus zero point 0.8, then it says that it's more likely that it's a no. So right here, let's say it's trying to detect cancer and saying that cancer is zero point 0.2 and then not detecting cancer is zero point 0.8, right? This right here is is how you can get an output out of this. Because once you know the output of this is zero point 0.2, 1 minus that is automatically the probability of not detection. So so now this right here is what we call a prediction. Prediction. So we're making a prediction that the outcome is some kind of Bernoulli distribution. Bernoulli distribution, right? But there is also the truth. The truth, let's say the truth is that the person does not have cancer. Therefore, the truth is saying that for 100% no cancer and 0% cancer. So this is the truth, right? Therefore, the difference between prediction and the truth is what we call the error. All right. So the distance, we can use that by measuring the distance between the prediction and the truth and let that be the error. So, how should we go about measuring the error, the distance between this distribution and this distribution? Well, from a previous class, you probably would have guessed that we would use cross entropy. With cross entropy, it allows us to measure the distance between two distributions, right? So these two distributions. And the equation for this cross entropy, which results in the error calculation, is that you find the information of Q using the probability of P. Okay. Now, so in this particular example, we have this is the Q is the prediction, and this is the truth. Right? Therefore, when we solve for the error, we simply find the cross entropy. And the result is, well, the first one is 0, 0 0.2, 0, 0 0.2, 1, 0 0.8, 1, 0 0.8, resulting 0.22. Okay, so this right here is essentially how you can calculate error for one sample. Now, of course, there are many, many samples in the data set, right? We are not just calculating one sample, we have multiple samples. So instead of just P of X or Q of X, we have P of Xi and Q of Xi. So it depends on the sample you put in. So the average error, what we do is we calculate the error for every single sample, all n samples, and then we divide by n to create an average. So, what was the equation for entropy? Well, the equation for entropy is P times the information of Q. Therefore, now we can split this out. When we split this out, then what we have is probability that x is equal to 0 times the log of our prediction, right? And then probability x equals to 1 times the log of 1 over our prediction, right? So once we calculate, this right here is the error for one sample, and then we loop through n samples, divide by n, giving us the average cross entropy error. In this example over here, we have three samples, right? Sample one, sample two, sample three. Therefore, you need to calculate the cross entropy three times and then divide by three. Okay, so for your first exercise, use base 2. See if you can calculate this. Okay? Pause the video, calculate it. I am going to move on. Okay, here's the solution. Hopefully, you are able to get it. All right, now that we got a better idea of what we're doing, we know that the sigmoid function is used as the probability that x is equal to 1, and 1 minus the sigmoid function, 1 minus, is the probability of failure that x is equal to 0. So now we can put all these equations together. Now, remember, we're trying to find the w that minimize the average error, right? Expected error. So that equation is 1 over n, and then of the entropy, cross entropy. So it's the average cross entropy. So we write the equation for the cross entropy out. So there are only two cases. The probability is equal to 0, x equals to 0, and the probability that x equals to 1. So there are only two cases. So for every single sample, you simply need to calculate this. Now, probability q equals to 0 is right here. So we can just plug that part in, and the probability that x is equal to 1 is right here, and we can plug this part in. So now this is the main objective. If this is what you want to solve, you want to find the w that minimizes the average error. Okay, the w. So the w's are here. This is what you want to find. Now, there isn't a closed form solution. Therefore, this is an example where you need to perform gradient descent. So you need to know how to take derivative of this. Okay. Now, to do this, you want to take the derivative. First, you need to simplify. So for your next exercise, you want to take, this is the expression we just have. What you want to do is you want to simplify it. For this exercise, you want to see if you can simplify into this. Like pause the video, take a couple moments. Once you can reach step 1, you want to simplify further into step 2. Okay. So for your exercise, see if you can identify how you can simplify this equation drastically into something that looks like this. Okay. The solution is in the next page. So this is how you do the first step. This is how you do the second step. Okay. So hopefully you are able to achieve that. So your ability to basically manipulate this equation mathematically is what determines whether you are be able to simplify it. All right. So once you have simplified, then the idea is easy. This is what we have done that we simplified. Once we simplify this, all we have to do is take the derivative. Okay, so for your next exercise, pause the video again. You want to see if you can take the derivative of this. Okay, pause the video. The solution is right here. So you should be able to go through this and figure out what the derivative is. Turns out that the derivative is really pretty easy to calculate. Okay, so like if you didn't perform all the simplification, it would be tough for you to reach this final derivative. So we want to make sure you understand how this is achieved. Okay, so this is the derivative that we normally use, right? For this class, of course, phi of x could be any set of feature maps. However, for now, we're just going to assume that everything is going to be a linear model so that everything is easy. So linear model is good enough, okay? So once we have the derivative, which is here, we simply plug it into the derivative, perform gradient descent, and the problem is solved. So logistic regression is really great because it is, if you think about it, an accumulation of everything we've learned this semester, right? Matrix and vector operations, right? We have to do that. Matrix and vector calculus all the derivatives we have to take. The idea of optimization, right? Specifically like minimization. The idea is supervised learning, right? And supervised learning divided into regression, classification, and that you understand the meaning of this function here, right? This is actually used for both regression and classification. You also needed to understand probability theory to know this, as well as probability notations, conditional probability, and as well as information theory. So we've covered a lot of ground for you to basically reach this point. Okay. All right. So for your final practice of the day, you have a couple points, right? Here's the data. What you want to do is basically write the code for logistic regression and then identify the theta or the weight that will make question correct. All right. So I provide the solution for you, but ideally you want to think through it yourself. Like think through it and only really look at the solution if you're stuck. Right. Now, performing that's with performing logistic regression raw, like without any special libraries. Okay, when you are outside working for companies, you can also use sklearn, logistic regression library, which is just one line. You call logistic regression, and then it gives you the weights, right, coefficients, and it also gives you the prediction. So notice the prediction 0011, which does a really good job doing the prediction. All right, as your last exercise, now that we did a really simple example, you want to load a really famous breast cancer data and perform binary classification on it. Okay, so this is how you get the data. Once you get the data, you want to make sure that you can do a pretty good job. Okay. All right, so this is it. I will see you in the next lecture.